Oh, I'll start recording now, but I will crop out later. There's just one person coming soon, but
Mhm.
shouldn't say just come in a minute. Yeah, that's the truth.
Also, you make like the stuff smaller as you see our
Yeah. They have changed the settings. I don't want to.
like Zoom update.
Yeah, Zoom updated. Why do they do this thing? I don't know. Uh,
Maybe it's the on, right?
okay. Immersive. What the fuck is this? I don't know. Why? Speaker? No. I think the problem is I popped this window out, so
No, it shouldn't be the case.
yeah, it wasn't the case before. I think they've changed something.
Uh,
I don't know. If I'll try this. Okay.
oh, we made this, yeah.
Okay. Right, is everyone's here? Okay, today we have Sangmin Choi from KU Leuven and here to speak on long-range interactions in celestial CFT.
From Amsterdam.
I'm so sorry, from Amsterdam. I'm so sorry.
No worries.
I got confused, my bad. On long-range interactions in celestial CFT. Please, thank you.
All right, thank you. Yeah, so thank you very much for the kind invitation to have the opportunity to speak. I haven't been to Brno so in person yet, so maybe at some point I wish I can make a visit. So yeah, today I'll be talking about some stuff that has some work that has culminated over the last 1 or 2 years with Alok Lada, Andrea Pum, and one of Andrea's students, Amia Kite. So um, let's begin. Oh, wait, before we begin, the topic will be long-range interactions in celestial CFT, but they're closely related concepts, one of which is asymptotic symmetries in asymptotically flat space-time, and another is logarithmic self-theorems in 4 dimensions. So I'll talk about these a little bit before jumping into the implications on celestial CFT, what this is, and the implications of long-range interactions. So let's begin. So soft theorem. What is a soft theorem? Soft theorem is a property of scattering amplitudes in gauge theories and also in gravitational theories in asymptotically flat space-times that can be derived using Feynman diagrams. So the statement is basically this. If you have some scattering of a number of particles with one of the external legs being a a boson, gauge boson, like gravitons or photons, and if you take the energy of that gauge boson to 0, then the amplitude factorizes very nicely. And you can write this in some series of this small energy scale of the gauge boson. And the leading term has a pole. And that pole usually is referred to as the leading soft theorem. And there's a subleading term, which at tree level is independent of this energy. And that's referred to as the tree level subleading soft theorem. And it is known that the leading term for abelian gauge theories and perturbative quantum gravity is exact to all loops. And then the order omega to 0 term holds at tree level. So I used the word asymptotically flat space time. So let me just talk a little bit about this. So this is a Penrose diagram of Minkowski space. And I consider a scenario where there's some number of particles, massive and massless, coming in from the past, making some complicated interactions and then scattering off to infinity. And massive particles come in from past time like infinity, which topologically is a hyperboloid. And then it also scatters to some future hyperboloid. That's the future time like infinity. And there's the null infinities where massless particles come in and the massless particles go out too. So what exactly are asymptotically flat spacetimes? We consider spacetimes that become flat as we go far away from wherever interaction is happening. So you can write the metric as some flat part plus corrections that are subleading in 1 over the radius coordinate. And here I've used retarded time to describe the spacetime near the future null infinity. But of course, you can use the advanced time to describe the past. Now, of course, we cannot use any corrections because we have to solve the Einstein equations. And this procedure was spelled out by many people in the 60s, including Bondi, van der Berg, Metzner, and Satz, who are collectively referred to as BMS. Unfortunately, the van der Berg got lost in one of the initials. And the solution is referred to as the Bondi coordinates. And you have the flat part here. There's some 1/r subleading corrections, one of which we recognize as the Bondi mass aspect. And then there's something called the shear in the angular directions. The capital letters I'll use to refer to the angular coordinates. All right. Now, we have a set of asymptotically flat spacetimes with different m's and different shears. And these form a set of asymptotically flat spacetimes. And you can ask the question, what is the symmetry transformations that map one solution to the other, or one asymptotically flat spacetime to another? And the guess back in the 60s was that it'll be, of course, the Poincare group. What else? But it turns out that that was not the case. And what turned out to be the symmetry group that preserves its structure is an extension of the Poincare group that's called the BMS group. And the extension is such that we generalize space-time translations into a transformation that depends on the angles. So you can think of the BMS, these extensions are called super translations in the sense that it extends translations. But unfortunately, the super has nothing to do with supersymmetry. It's just a name that got stuck over the years. And these super translations are essentially some angle-dependent translations that are generated by this vector field. And you can see that because there's a function of the sphere worth of transformations, you can decompose it into spherical harmonics. So there's an countably infinite number of generators. So this forms an infinite dimensional group. So since we have generalized super translations, you could ask, well, can we generalize Lorentz transformations? And of course you can. So you can write down a vector field on the sphere, and you can think of diffeomorphisms generated by this vector field. And a special case of these transformations is, of course, the Lorentz transformations. But now I want to generalize this to not only these 6 global coordinate transformations that are defined in the sphere, but also more generally just smooth diffeomorphisms on the sphere. Now, if you do this, we have an extended group of the BMS group. This is usually referred to as the generalized BMS group. And it consists of super translations and super rotations. And nowadays, people don't go through the trouble of adding the word generalized. And whenever people talk about BMS, they usually just include super rotations as well. So any questions up until now? No? All right. These BMS transformations are symmetries of flat space quantum gravity. And as a low energy effective field theory, we know how to compute S matrices in gravity around flat space. So we basically expand the metric to be the flat space plus corrections. And this correction represents the graviton degrees of freedom. And what do we mean that these are symmetries of gravity? We mean that these BMS charges must be conserved, but these are not exact symmetries. These are asymptotic symmetries in the sense that they preserve the asymptotic form of the metric or the asymptotic structure of the metric. So they must be conserved, but not every not at every Cauchy slice in the bulk. They're conserved at the very infinite past and at the very infinite future. And what that means is that they are a conserved charge in scattering processes. And what I mean by this is if you measure the charge in a scattering process of the incoming state, that must be in agreement with the charge in the outgoing state. So in that sense, the charge must commute with the S matrix. Now, that sounds all nice, but this is an infinite symmetry group. So this presumably imposes an infinite number of new constraints that generalizes the energy momentum and angular momentum conservation laws. So is this like compatible? We seem to have found an infinite number of new conservation laws that constrain the gravitational S matrix. It turns out that these are not new constraints, but they are just a rewriting of the constraints that we already know. And these are actually the rewritings of the soft graviton theorems. So if you take this equation here, plug in all the expressions for the charges and compute the S-matrix, the scattering amplitudes, then you'll find that actually that exactly amounts to the leading soft graviton theorem. So what that tells us is that the soft graviton theorems are conservation laws of the supertranslation symmetry. Now, over the past decade or so, a huge, yes,
Can I have a question there?
yes,
So you say that the BMS group is infinite dimensional. So then I would assume that there should be infinitely many conservation laws.
yes.
Can you point out where the infinity now pops up in these?
Yes. So when you say there is an external graviton that gives you the soft graviton theorem, you have to specify the momentum of the graviton. That degree of freedom is infinite. You have to pick a direction on the sphere. And each direction corresponds to a delta function degrees of freedom in the when you so you can decompose any smooth function on the sphere into a sum of delta functions over each point on the sphere. And each of those points correspond to each direction that you can choose for this soft graviton.
Thank you.
Yep. Yeah. So there has been a lot of development over the past decade to identify these correspondences between soft theorems and asymptotic symmetries, case by case in different gauge theories and gravitational theories. So, for instance, in gauge theory, in abelian gauge theories, you want gauge transformations that don't vanish at infinity. So, if you, for instance, take just a function on the sphere, those do not vanish at infinity. And if you follow the Noether procedure to compute the charge, you'll find that there is a process where you partial integrate that introduces a boundary term. And if the gauge parameter doesn't vanish at infinity, that charge is not zero, and therefore they have a non-trivial action on the states. So that means that it's physical, and it turns out that the conservation law corresponds to the leading soft photon theorem. And these, you can work out different cases, although you have to do this at the moment by case in different theories. But this correspondence seems fairly robust, like gauge theories, gravitational theories, leading soft theorem, subleading soft theorem, not only 4 dimensions, but higher dimensions. Also, if you include supersymmetry, there's soft Fotino theorem, soft Gravitino theorem, and so on and so forth. Now, in the recent years, we have found a new soft theorem, and I want to talk a little bit about that. So in 2014, there was a group at UCLA that have computed the subleading soft behavior of gluons and graviton amplitudes. And they found that if you go to loops, then you have a modified effect in addition to the known effect at tree level. But the problem is that that correction that comes at one loop is infrared divergent. So they worked in 4 plus epsilon dimensions. And the correction to the subleading soft factor seemed to come at a power of 1 over epsilon. And this is problematic because we thought we have factored out all the infrared divergences by picking out the 1 over omega factor. And then whatever comes next, we thought was finite, but we cannot take epsilon to 0 because that correction becomes sick. And what this implies is that the loop integrals, which do not contribute to the leading pole, still include some divergences, leftover divergences that haven't been factored out. Now, a few years later, Sen and his collaborators Lada and Sahu have shown using massive QED and massive scalars coupled to gravity in 4 dimensions, not 4 plus epsilon, that there must be a non-analytic term in the soft behavior if you compute loop diagrams. And that non-analytic behavior comes as a logarithm in the soft graviton energy. So actually, in between the 1 over omega and omega naught, there's an additional term that's non-analytic. Now, this is very suggestive of the work in 2014 because if you take this log omega term and take the massless limit, you exactly reproduce the coefficient of 1 over epsilon that Byrne, Davis, and Noel have seen for graviton amplitudes in 4 plus epsilon dimensions. This seems to tell us that the leftover infrared divergence that these people observed in 4 plus epsilon dimensions was the logarithm. And of course, you cannot see logarithms in non-integral dimensions. So this is a peculiar feature in 4 dimension only. Just to illustrate what the soft vector looks like, the coefficient of log omega sitting here looks like this. It's a bunch of sum over pairs of particles in the external states, where almost all the things are written in terms of the relative velocity between pairs of particles. And just to contrast the difference between the log and the other soft vectors, this is the leading soft vector, and this is the tree-level subleading soft vector. So you can see that somehow the logarithm, the coefficient of the logarithm is much more complicated compared to the other terms. So we have found a new soft theorem, and we now understand that soft theorems come from the conservation laws or identities of asymptotic symmetries. So the question that naturally you can ask is, what is the asymptotic symmetry whose conservation law gives you this? So this was the work that Andrea Alok and I have been working on for the last 2 years. And the setup is this. So we consider a theory of massive scalar particles coupled to gravitons. So we take the metric to be flat plus corrections. And because we have massive particles, we have to decompose the time like infinity into the hyperboloid. And in order to do this, we take the following hyperbolic coordinates. This is analogous to the big Schmitz coordinates that are used to blow up the space like infinity, if anyone has worked on the behavior of asymptotic particles at space like infinity. And since we also have massless particles, which are the gravitons, we also have to work with null infinities. And you find that the superrotation at null infinity is parameterized by a vector field. And the supertranslation that was written in terms of the vector field on the sphere on null infinity, you can extend it into the future time like infinity by using a bulk to boundary propagator. And this is standard thing that you can do in ADS CFT. It's just that now the hyperboloid is much less like a Euclidean ADS3 slice. And what I will show with this setup is that the log soft graviton theorem is the word identity of BMS superrotation when you include long-range interactions into account. Okay. So we have to compute the charge, and we have to do this on a Cauchy slice. And that Cauchy slice we take to be the one at the infinite far future. So the Cauchy slice consists of the future time like infinity and null infinity. And the contribution from the future time like infinity has to do with the massive particles. So we call this the hard charge. And because it's basically a diffeomorphism generated by the vector field on the hyperboloid, it can be written in terms of the contraction of the stress tensor with this vector field. Now, it is known at tree level, the massive fields fall off as 1 over tau 3^2, where tau is the hyperbolic time. And then something terms that are subleading in 1 over tau. And this tells us that at tree level, the energy momentum tensor falls off like 1 over tau cubed. So this is a finite number, of course. But the problem is that fields are not free at infinity because there are long-range interactions that are generated by the graviton interaction. So to find the asymptotic fields at future time like infinity, we take the Einstein equations and the Klein-Gordon equations, and we solve them order by order in the coupling. One finds that the solution to the Einstein equation has the time component of the graviton falling off as 1 over time. And the coefficient is some form that people may recognize coming from gravitational memory effects, that the Green's function is given in terms of the geodesic distance between 2 points on the hyperboloid. And because of this presence of the graviton at future time like infinity, by the way, at time like infinity, free massless particles don't propagate into it. So you could guess, well, it's time like infinity, so there's no gravitons. But actually, because of the massive scalar fields generating the graviton, the sourced graviton, this is the field that exists even at time like infinity. And then now this couples to the Klein-Gordon equation and generates a correction to the free field solution of the scalar field. And it turns out that correction becomes a phase. So at leading order in the coupling, it becomes I times log of time times this graviton field. And you can do this order by order, and you'll see that this thing exponentiates to a phase. And not only does it exponentiate to a phase, it exponentiates to a divergent phase. And as a consequence, when you plug this into the stress tensor and use that stress tensor expression to compute the charge, you'll find that the charge diverges as we take time to infinity, because this is a future infinity. So we have to regulate this. So this is infrared divergence. So the regulation you can do as thinking of putting the system in a box. And that scale of the box you take to be the energy scale associated with that distance, you take to be lambda. So the distance, the tau, you can think of as lambda inverse. So the charge for the superrotation, including long-range interactions, has a log of lambda inverse divergence, and the coefficients take some form that is written in terms of the sourced graviton, the matter scalar field operators, and the vector field y bar. Now, this correction, because it involves explicit factor of the coupling times the sourced graviton, which also carries a factor of kappa, it is a correction that is higher in 2 powers in the coupling. So in that sense, this is like a one loop correction to the charge. And you can find that you can do this analysis order by order to all orders, and you'll see that there's no further corrections. This is a one loop exact correction to the charge. So that was the contribution to charge at time like infinity. We also have to compute the contribution at null infinity. At tree level, the superrotation charge at null infinity is known to have the following form, where we recognize the shear tensor and the vector field on the sphere. The shear tensor, if you take the retarded time to be very large, you'll find that it reduces to some constant, and then something that falls off exponentially fast. Now, at tree level, you see that there's a factor of u, a derivative in u, with the integral over the null infinity. And in momentum space, this reduces to the following projection in energy space. And you can act this on a series in powers of the energy, and you'll see that it picks out the energy to zero term in the power series, which tells us that the soft factor sort of picks up the omega independent term in the soft expansion, which exactly corresponds to the tree-level soft graviton theorem. Now, long-range interactions change two things in this picture. Just like the matter fields, the graviton fields also live on scry, and they acquire a gravitational dressing. And matter interacts with gravitons at the future boundary of scry, which affects the large positive U behavior of this shear tensor. So let's look at the dressing first. So just like how the scalar field obtained the phase because of the presence of the source graviton, the graviton also acquires a phase, and that phase, because there's only a one loop effect coming in, you'll find that the phase only contributes to one power in kappa as a shift. Further corrections like kappa squared and kappa cubed and so forth, they will contribute to higher order in the soft expansion. Now, this graviton can be written in terms of the scalar field and the vector field in some particular way. But yeah. Well, an easy way to see it, well, of course, you can compute this divergence or divergent factor or the shift by solving the Einstein equations, which is the hard way. Another way you can do this is you can couple a scalar field to gravitons at null infinity. And you'll find that you can couple a gauge field, U1 gauge field, to gravitons at null infinity. And you'll find that the gauge field gets dressed, or the gauge field acquires a gravitational dressing. And you can invoke the equivalence principle that gravitons couple to all matter in the same way. So the way that gravitons get dressed should be exactly the same way as the gauge field gets dressed. And you can obtain this shift in that way. So the shift nets to the soft charge getting the correction that is of order lambda, log of lambda inverse. Now, we have massive matter at time like infinity, and the time like infinity talks to null infinity at the future boundary. So you can solve the Einstein equation at this boundary to find that the shear gets corrected when you take u to be positive infinity by some 1 over u times some powers of log u. And you'll see that every power of log u in principle could be there, but Einstein equations tell you that the only term that is non-zero among these coefficients is the one that doesn't have any powers of logs. And at the end of the day, you'll find that the shear, when you take u to infinity, has a constant term that was present at tree level. And at tree level, the next correction was exponentially fast falling off. But now we have a 1 over u correction. So remember that we had in the soft charge, we had a factor of u and a derivative of u combined with the integral over null infinity. And if the shear falls off as 1 over u at large times, that introduces a divergence. So you again have to regulate by putting the system in a box. And that scale you take to be lambda inverse, and you'll find that this interaction of this shear with matter at the future of time, like the future of null infinity, gives you another log lambda inverse correction. And collectively, you'll see that the soft charge is again divergent logarithmically, and the coefficient is given in the following. And again, this expression is one loop exact in kappa. Okay, so we computed both of the contributions on the Cauchy slice, so we can combine them to get the full charge for the superrotations. And the charge is divergent logarithmically in the cutoff, and we have a hard contribution and a soft contribution. So the statement of charge conservation or ward identity is that this charge commutes with the S matrix. And that conservation law amounts to something that is divergent because the charge itself is divergent, plus some finite terms. And we are saying that this commutator is zero. So we have a divergent term equal to zero. So it better be that the coefficient of the divergence be zero. And you'll find out that the operator, the projector that appears here, derivative with two powers of energy with another derivative in the limit where the energy goes to zero. If you write down a series of soft expansion with logarithms, you'll see that this picks out exactly the one term that has a single power of logarithms and nothing else. So the ward identity of superrotation with long-range interactions taken into account exactly reproduces the log soft graviton theorem. Yeah, and the projector kills off any other terms. So any questions here so far? If not, let's move on. So what have we learned? We have learned that, well, it was known that at tree level, BMS superrotation symmetry led to the tree level subleading soft graviton theorem, which was at order omega to zero. Now, if you take long-range interactions into account, the charge becomes divergent, and the associated ward identity becomes the logarithmic soft graviton theorem. So now we want to study what these findings imply on the celestial CFT. So let's turn the gears a bit and talk about those. So what is a celestial CFT and what is the celestial business that the celestial community is talking about? So the idea is that you can take the momentum space amplitude and perform a Mellin transform on all of the energies of the particles. That'll put you from a momentum eigenstate basis to an amplitude written in terms of the boost eigenstates. Now, if you do that, then of course, because you no longer have the notion of soft energy, you'll have something different. So now the soft theorems or the soft vectors manifest in the Mellin space as operators that are defined as residues of poles. So for instance, if you take the momentum space amplitude and do the small omega expansion, you find that the leading term was the leading soft graviton theorem. At tree level, the next term was omega to zero. That was the tree level subleading soft theorem. And there will be a subleading soft graviton theorem, subleading, and so on, until at some point the soft theorem no longer holds and the amplitude doesn't factorize. Now, in Mellin space, in the celestial amplitude, these theorems can be written in terms of some soft operator that has very much to do with the soft graviton operator that we have seen earlier, that appears as a residue of pole in the space of this complex number delta. And the tree-level subleading soft theorem appears as a pole at zero. The subleading soft theorem appears as a pole in delta x minus 1. So you can see that this goes from 1, 0, minus 1, minus 2, and the number just goes on. So what about these soft operators? These soft operators now are conserved currents in the putative celestial CFT, which gives rise to ward identities. And what I mean by that is, for instance, if you take the leading soft graviton theorem, the soft operator you can write as the residue of the pole at delta equals 1. You plug that into an amplitude in the putative CFT, and that'll give you a ward identity in the sense that it'll give you a factor times sum over the rest of the insertions. Of course, this is the Oh, sorry, there is a typo here. This is the soft photon theorem. There's also the soft graviton theorem, which takes a different form that depends on the energy of the particles and so on. But the idea is that in this putative celestial CFT, which by the way, we have not found yet, we can write all the soft theorems can be written in terms of some word identities of some conserved current that is associated with the soft boson operator. Now, the OPEs of soft operators can be derived by taking consecutive soft limits. And these OPEs reflect the algebra of the asymptotic symmetry. So for instance, in gravity, we know that the asymptotic symmetry is the BMS symmetry, and they are associated with the leading and subleading soft graviton theorems. So what does it mean? The BMS algebra tells us that supertranslations commute. A supertranslation followed by a superrotation gives you another supertranslation. And two superrotations give you a third superrotation. Now, if you take this algebra and compute the word identities, you'll find that, of course, the soft operators that are associated with the leading soft graviton theorem commute. This is the statement about supertranslations commuting. The OPE between a soft operator for the leading soft theorem and the soft operator for the tree-level subleading soft theorem, the OP gives you another soft operator with, I should have not have tree here, an operator that has to do with the leading soft graviton theorem. This is the statement about supertranslation followed by a superrotation, giving you another supertranslation. And the OPE between two operators that are associated with the subleading soft graviton theorem gives you another one of those operators with a bunch of dressings that have to do with exactly how the third superrotation comes in. But you can see that these OPEs between soft algebra encodes the information about the algebra of the asymptotic symmetry. So this is all established at tree level. Now we know that logarithmic soft vector is there once you include loop effects. And if you Mellin transform logs, you'll find that whenever you have powers of logs, any poles in the Mellin variable becomes higher in order. In particular, the logarithmic soft theorem, which goes like log of omega, if you Mellin transform this, then the soft operator, which we'll call O of one loop, this is a residue of a double pole at lambda equals 0. So this supersedes whatever singularity you are seeing at the delta equals 0 at tree level. Now the question you can ask is, how does this one loop correction modify the soft algebra? And this was the question that we were tackling in the paper that came out this year. So the idea is this. In the line of computations that we have done associating logarithmic soft theorem to the BMS superrotation, we have learned that the corrections make the charge divergent. And the coefficient of the divergence generated the log soft theorem as a word identity. And therefore, this is the operator that corresponds to the residue of the double pole at delta equals 0. So we take this superrotation charge, which has been corrected infinitely, and we compute the BMS algebra. And we'll see that the Lie bracket between this correction with another correction should be 0 because it should give you a third superrotation, but superrotations don't have two powers of logs. So this should be 0. The bracket between the finite term, the bracket between the finite term and the logarithmic divergent term should combine to give you another term that is logarithmic in lambda inverse. So that should give you the coefficient of the third superrotation.
Can I have another question?
Yes.
So lambda is an infrared regularization, right?
Yes.
Do you have any UV regularizations?
Oh, no. UV, we are not considering in these computations. We will think of those as being taken care of.
Okay. And I guess you're only talking about perturbative in kappa. I
Oh,
would
yes.
imagine.
We are doing everything perturbatively. We cannot do any, you cannot make any non-perturbative.
If you go 2 slides back, then you have a 1 over kappa. How am I
Oh,
supposed? Yeah,
you
so you
mean
have
these things?
yes. So that looks non-perturbative to me. Or can you?
Oh, actually, yeah. So the origin of this 1 over kappa squared comes from the action where we have a 1 over 16 pi g Newton.
Right.
Yeah, so this comes from there. And actually you'll see that the shear, the shear, so the shear was the correction to the angular part of the metric. So this is linear in kappa. So there comes one kappa here.
I see. There's some implicit kappas.
Yes, there's some implicit kappas, and at the end of the day, you'll find that the soft charge can be written as a 1 over kappa times something. And when
Thank
you
you.
write down the word identity, you multiply all sides by kappas, and thereby the logarithmic soft theorem will come with 3 powers of kappas.
Thank you.
Yep. Okay. Yes. So from the fact that we learned that superrotation charge gets divergently corrected, we learned that the coefficients should have the following brackets with all the other terms. And this should be reflected in the OPE between this new operator that appears at one loop as a residue of a double pole with all the rest of the operators in the CFT. And this is exactly what we find. The fact that two superrotation corrections commute comes as the OPE between two of these new operators being zero or regular. And the tree level operator at delta equals zero, this is the operator associated with the tree level superrotation. Its OPE with one loop is another tree level. Oh, is that a typo? Yes, I am sorry, that's a typo. That should be a one loop to reflect the fact that Q naught and Q log gives another Q log. So the operator on the right is one loop. That is a typo. And the operator associated super translation, its OPE with this new operator is zero. That reflects the zero bracket. Now there is a subtlety here. The second OPE can only be derived in one order of limits. Remember that we derive these OPEs in consecutive soft limits. So you insert two gravitons, and you have to decide which one you take to be solved first. And there seems to be a particular preference for an order of limits. And this preference of order of limits is not new in this context. This can be also found in other theories like non-abelian gauge theories, where the preference of some order of limits has to do with some physical issues. And that at the moment we have not completely understood yet. So we are expecting that we understand some physical reasons behind this preference in the near future. But at the moment, we take note that the second OPE, which is consistent with the BMS algebra, can only be derived in a particular order of limits in the consecutive soft limits. Okay, so that was the leading logarithmic soft theorems, so to say. And those log soft theorems have been derived in 2018. Now, over the past years, it has been conjectured, and some of the leading ones have been derived even, that an infinite tower of universal log-soft theorems exist, each of which are nth loop exact. So what that means is if you take the n plus 1 point amplitude with a graviton, of course you have the 1 over omega pole, and the result of 2018 was that there's a logarithm afterwards. Now the conjecture is that there is an infinite tower of these, each of which gets an additional power of omega times log omega. And the first one is tree exact in the sense that the tree level result doesn't get corrected. The first log is one loop exact. There's no two loop and higher corrections. The third term is two loop exact, and so on. Now, I think the exactness has been proven to these three orders, and universality, I think, also has been proven to these three orders. But it has been conjectured that the computation seems fairly systematic that you can do it to all orders. At the moment, this has been studied in various papers, and all of these are classical at the moment. But the fact that you can obtain the first and second corrections with Feynman diagrams seems to suggest that there must be also quantum counterparts, which are fairly straightforward extensions of the classical results. And of course, there are non-universal terms, which include the tree-level results that may factorize or may not, and those I have not written down explicitly. Now, we can use the methods that we have used to study the log soft theorem to study the higher orders. Oh. And we find that the charge whose word identity has n powers of logs has a divergent structure that can be written as a sum over powers of the IR regulator. Now, from the conjectured infinite tower of log soft theorems, you'll see that it is the one whose word identity generates the soft theorem is the coefficient of the leading divergence. And in the celestial CFT, you can associate this coefficient with the soft graviton operator that comes at n loops as the residue of the n plus 1th order pole at delta equals some integer that's a function of n. And it's important that it's only the leading one. And you can compute the OPEs between these powers, these operators, and you'll see that the OPEs vanish. Now, you could ask, well, does it mean that the soft algebra is abelian? And we have seen that that is not the case because at one loop, we saw that the leading operators, the OP between two corrections vanished, but that didn't mean the BMS algebra was abelian. So in order to say something concrete about the entire soft algebra after loop corrections, it seems like we need all the corrections to the divergent structure of the charge, which come from soft theorems that may not be universal. Yeah, and that is something that seems to be very puzzling, but this is something that we are planning to work on in the future. So yes, that is it. Thank you for your attention.
Are there any questions from the audience? You might want to come closer, but yeah, I forgot to connect the real speaker.
Hi, can you hear me?
Hello. Yes.
Yeah. So the question is about when you were setting the coefficient of the log lambda to 0 before the celestial.
Yes. I guess here,
Yeah.
right?
Yeah.
Yes.
Yeah. I mean, this just seems to be a basic confusion. So in here, you're working with a hard IR cutoff, right? Lambda.
Yes.
So, I mean, I'm a bit confused then how can we take the limit omega tends to 0? Because this seems to be in conflict, right? Because if I have a hard IR cutoff, then
Yes.
the photon momenta can really not go to, it cannot have zero energy.
Oh, yes, yes. So yes, that's a good question. Thank you. So when we say soft theorem, it is convenient to think of it as an expansion around omega equals 0, but that's not actually what we are doing. What we are actually doing is the soft theorem is not a statement about the energy of the graviton or photon going to 0, but rather it's a statement about the regime in the kinematic space where the graviton energy is much less than all the rest of the particles. So the graviton energy could, for instance, be like 10 TeV, which is very high, as long as the rest of the legs, the scalar fields coupled to graviton, have much more higher energy. So in that sense, yeah, you can think of this as being expanded around the IR cutoff. So let's say we also have the infrared cutoff in the momentum space to be lambda. Then we will expand omega around lambda,
Mhm.
and that is fine because the infrared cutoff will be much smaller than all the rest of the particles.
Yeah, but still, when you are taking the
Yes.
limit omega tends to zero, at some
Yes.
point you're going to run into problem with lambda, right?
Oh yeah. So the my answer to that was that we although it's the convenient way to write things, this is not actually what's happening. So we are not actually taking the energy of the graviton to zero. We are thinking of it to be very small.
Hmm. Because okay, so there is a different way of thinking about the soft theorems without alluding to the asymptotic symmetries, right? Which is essentially using the general coordinate invariance for the soft gravitons or the gauge invariance for the photon,
Yes.
right? And that gives me an universal structure. But the point is that both of those symmetries typically is in tension with an IR cutoff. So typically what we do in d equals to 4 is that we put a soft photon mass or a soft graviton mass, or we put it in a box, but then we know that the S matrix is not the correct S matrix, so to speak, but the inclusive cross section is independent of this and
Yes.
things work out perfectly fine. But
Hmm.
here you're trying to extract a statement at the level of S matrix directly, right? You're not working at the inclusive cross section.
Oh
So
yeah. So this is a statement about amplitudes.
yeah,
Yes.
exactly. So it means that this is a sort of a cutoff dependent statement. So to argue that the coefficient of log lambda is zero, it seems to
Hmm.
me that there is a because eventually I would like to take the higher cutoff to infinity as well.
Yes.
So in that sense, there is a sort of a subtlety, right?
Yes, yeah. So I guess this is also tied, as you mentioned, to the fact that the amplitude actually doesn't exist unless you put a cutoff, right?
Yeah,
Yeah.
exactly.
I guess one way to circumvent this is of course, the standard Bloch-Nozick way, as you mentioned, the inclusive cross-section will give you something IR finite. But
Right.
another way is the IR divergence actually comes from using the wrong states.
Yeah.
So yeah,
I
you can also use these like so-called Faddeev stressings to
yeah.
make the S matrix itself well defined. And I actually think that's the right way to do this. And
Maybe just as an alternative, could you also maybe try to do it with the Schwartz Hannes dotted proposal for the higher finite S matrix?
ah,
Because Matthew Schwartz and his student
yes.
few years back, they gave a
So
proposal for an higher finite S matrix as well.
is that in alignment with using dressed states? I would imagine so, right?
It's not very clear what the correspondence is, because
Yes.
for Fatih Kulish, you know much bit more than me, but it seems like in Fatih Kulish doing an exact S matrix computation is quite hard. The principles are very clear.
Yes.
You have to use the correct asymptotic states, the Dre states, and
Yes.
etc. But I think the Schwartz Anistotle had the advantage that you can actually do the computations using the textbook principles, but you have to define this new S matrix, which is now, by construction, I have finite.
I see. Yeah, actually, very little has been understood about logarithmic self theorems and the
Mhm.
IR
Yeah,
divergence associated with those.
right.
That seeing any formalism other than the standard textbook S matrix, which is done here, would be
Mhm.
very interesting. And actually, there's a guy at Luke Stiplo, I think that's his name. He's working with scattering amplitudes at finite time. So
Mhm.
he's looking at infinite time, but he's not using the perturbative theory. He's more
Ah.
or less looking at just overlaps of states, in the efforts to not work with these IR cutoffs at all.
Mhm.
And I think he's also like stepping into the direction of writing these kind of stories in a more mathematically rigorous way.
Mhm. I
But
see.
yeah, so that's one direction, and of course the Faddeev stressing how you can write down these amplitudes using dress states like the well-defined S matrix amplitudes, which you have to work with actually, or I guess this other uh Schwartz Matthew Schwartz's way of writing things, which I don't completely understand, but which I feel like they are much in line with what Faddeev and Cauchy were doing.
Yeah, definitely the same principle, but
Yeah,
the technical details are quite
right.
different. So
Yeah, and any of these directions I'd be very interested to see. But you can think of this as like the first stepping stone towards something more rigorous because, after all this work, you can say, well, that's all good work, but S matrix doesn't exist with the standard S matrix, the textbook way of writing things, right? So
yeah,
yeah.
yeah,
So
sure. Yeah.
I understand the sentiment that
No, no, I mean,
this
yeah,
is
I've asked the same question to Alok, so I thought I will ask you as well.
yes. Yeah, Alok's also thought hard about like how to write these things with dressed amplitudes.
Mhm.
Yeah,
Yeah.
he's shown me some like crazy amount of notes, but I think at the moment very less has been understood in this direction using these more sophisticated ideas. Yeah.
Right. Thanks.
Yeah, no worries. Thank you.
If there are no more questions, let's thank the speaker again.
Yeah, thank you.
Thank you.
Well,
Bye. Thank you.
you can stop the recording.
Yeah, I'll stop the recording.